7c. Net forces, the force remaining after all other forces have been cancelled out. Before we can spend time talking about net forces, it is important to discuss free body diagrams. These are simple illustrations showing all the forces that are acting on an object, body, or mass. Remember, forces are vectors, so equal and opposite forces will cancel one another out. If all forces balance out, then there is no unbalanced or net force. This means that the object will remain still or remain moving in a straight line at a constant speed as per Newton's first law. If the forces do not all balance out, then there is an unbalanced force or a net force, and the object will accelerate, which means it will speed up or slow down or change directions. The principal types of forces in Physics 11 are gravity, friction, normal, and applied forces. This book resting on a table can be drawn simply as a box. I have labeled it as a mass, but object, body, or book would also be suffice. Now with free body diagrams, we need to draw in all the forces that are acting on the book, which we'll represent with arrows. Since the book is not moving, it's not accelerating, and not changing directions, the forces should all cancel out. The first force we can draw is the force of gravity, which would pull the book down. Since the book is not falling due to gravity, there must be a support force holding the book up, which in this case is called the normal force. This is perpendicular to the tabletop, so it's straight up. There are no side forces acting on this book. Next example is a skydiver. I'll represent him as a square. The obvious force acting on him again is gravity, which is straight down. Now if we assume that there is air, then there may be an air friction force acting on him upwards to slow him down. Notice how I drew the air friction force shorter. This means he is accelerating downwards, but less than negative 9.8 meters per second squared that we would see if he was in a vacuum. This flying squirrel is gently gliding down at a constant speed. Again, a box for the squirrel. The force of gravity is downwards. In this case, the speed is uniform, which means there is no acceleration. The normal force is equal but opposite in magnitude to gravity, so the arrow is the same length but upwards. This man pushing the rock can be represented by a box. There is a force of gravity acting on the rock. It is not dropping, so there is a normal force equal to Fg that supports the rock. Now the man applies a force to the rock to the right, which is the black arrow. Since the rock does not move, there must be an equal force acting on the rock to resist the motion, which is friction force, the blue arrow. This gymnast is suspended from the rings. He also has gravity acting on him. If he stays suspended, completely motionless, then he also has a force similar to normal force. Since this force is along ropes, we call it tension force. However, there is not only one rope, there are two ropes. So there's two forces of tension acting on the gymnast to suspend him. This cart is being pulled by the horse. We can draw the cart as a box. There's a force of gravity acting on it. There's a normal force keeping it from falling into earth. And the horse is applying an applied force in an attempt to move the cart. If friction force, that is acting in the opposite direction to the applied force, is smaller than applied force, then the cart will move. In this case, the friction force arrow is shorter than the force applied arrow, so the cart should move. Now for net force. This is the force remaining after all the other forces have been cancelled out. Forces are vectors, so they may be represented by vector diagrams. In this diagram, it looks like there are two forces acting on the mass, one pushing and one pulling. Since they're in the same direction, the forces add up to 7 newtons to the right. The object should accelerate to the right. In this vector diagram, the forces are in opposite directions, so the 2 newtons to the left cancels out the 2 newtons on the right. This makes a net force of 3 newtons to the right. This mass should also accelerate to the right. For this object, the up and down forces oppose each other with the same magnitude, meaning that they completely cancel each other out. The net force is 0 newtons. This object will remain stationary or will remain moving in a constant speed in a straight line. This mass has 2 perpendicular forces acting on it. The net force would be this red arrow. We can solve for the red arrow using trigonometry. This object will have a net force of approximately 6.8 newtons and accelerates at an angle of 26.6 degrees at an incline to the right. This mass has 4 forces acting on it, but the horizontal forces are equal and opposite, so they cancel out. The down force of 6 newtons cancels out 6 newtons of up force, leaving a net of 5 newtons upwards. This object will accelerate upwards with a force of 5 newtons. This object has 3 forces acting on it, 2 pulling to the right. This makes an 8 Newton force acting to the right and a 6 Newton force acting to the left. The net force is 2 newtons to the right, and it will accelerate to the right. This one is similar to the last, where there are 3 forces acting on it. 2 are acting in the same direction up, which makes 12 newtons of force upwards. This is countered by the 12 newtons downward, so the net force is 0. This object will have zero acceleration. It will stay still or keep moving at a uniform speed in one direction. To summarize, there are two results in dynamics. If the net forces acting on an object is zero, the forces are balanced and the object will stay at rest or continue moving uniformly in one direction. It does not accelerate. If the net forces do not equal zero, then the forces are unbalanced, which means the object is speeding up, slowing down, or changing directions. It is accelerating.